Hello everyone. We begin with Module 3, that is the Indigenous Sciences and Mathematics. Now, before we begin Module 3, let's just take a quick look at Module 2.3, the Lesson 2.3, where we talked about the Nyaya School of Learning. So, according to the Nyaya School of Learning, there was a typical proof theory that they followed. So, what did the proof theory had was the initial was Anumana. So, in Anumana, there was Pratigna, there was Hetu, there was Udharana, there was Upanya, and there was Nigamana, the conclusion. After that, it went on to talk about Vyapti. Vyapti was conscious deliberation, in which there was Hetu, there was Upadhi, and there was Vyapaka Sadhya. And it was only after this deliberation that a true and a false theory was propounded on. And true, and if it was true, it was accepted, and if it was false, it was rejected. So everything there had a realistic logic to it, which need to be followed. And that is what we are supposed to do now in the basic learning system, be it any subject, any field. So it is more like a holistic encounter to the learning outcomes that we have. Now we begin with Module 3, that is Indigenous Sciences and Mathematics, Lesson 3.1. Here we are going to talk about Sulba Sutra and geometry in altar construction, Aryabhata and Bhaskara, the algebra and the astronomy gurus. Let's begin. So, Sulba Sutra and geometry in altar construction. So, the Sulba Sutra or Sulba Sutra are ancient Indian Sanskrit texts that are appendices to the Vedas. They are attachment to the Vedas, specifically belonging to the Srota ritual. Their primary focus is on providing the geometrical principles and construction methods necessary for building various fire altars, Vedi and Agnisyana, for Vedic sacrificial rituals. So, altars in olden times were made for sacrifices, and all these altars we will see that they were very carefully and rigorously planned. None of them were haphazard, everything had a perfect dimension, everything had a perfect structure. Here's how the Sulba Sutra relate to geometry and altar construction. So, first is the practical geometry for rituals. The success of a Vedic ritual was believed to depend heavily on the precise construction of the fire altars. This meant that the altars had to conform to very specific measurements, shapes, and areas. The Sulba Sutra served as detailed construction manual outlining the steps and principles for creating these altars. They were not abstract mathematical treatises, but practical guides for masons and priests. That is how, if you see that the temples, the altars, all of our older ones are so appropriately and so meticulously created. Every measurement was taken very appropriately, every angle was measured very appropriately, so that the structure could be as required for all the rituals that were to be performed over it. Key geometric principles and discoveries. The Pythagorean theorem, the Sulba Sutra, contain clear statements and applications of what is known as the Pythagorean theorem. I'm sure some of us may be aware of the Pythagoras theorem that we've been reading in the basic maths text that have been there in middle schools or in senior schools. The square of the diagonal of a rectangle is equal to the sum of the squares on its two sides. I hope you remember that. This knowledge predates Pythagoras by centuries, with evidence found in texts like the Bodhayana Sulba Sutra. They even listed Pythagorean triples, example 3, 4, and 5, and 5, 12, and 13. Area preservation and geometric transformations. A crucial aspect of altar construction was the ability to transform one geometric shape into another while maintaining the same area. For example, the Sulba Sutra describes methods for constructing a square equal in area to a given rectangle, constructing a square equal to the sum or difference of two given squares, squaring the circle, and vice versa, which involves geometrically constructing a square having the same area as a given circle and vice versa. Means the square and the circle have the same area despite of the difference in shape. They were approximate methods but demonstrated a sophisticated understanding of the area. Now here in the figure that you can see is the Pythagoras theorem, which says a square plus b square is equal to c square, which we have just seen how the Pythagorean theorem varies. Irrational numbers. The practical constructions, especially involving diagonals of squares, led to an understanding and remarkably accurate estimation of irrational numbers like the square root system. Basic geometric constructions. The sutras provide methods for drawing perpendiculars using intersecting circles, bisecting lines and angles, constructing various regular polygons, establishing cardinal directions, the east-west line using sun shadows. How we see sundials and sun watches, even Jantar Mantar is an example of the same. Diverse altar shapes and their significance. Now, every altar had a dedicated purpose. Hence, the altar shape varied according to its purpose. Different ritualistic purposes were associated with specific altar shapes, all while maintaining a consistent overall area. The area would remain the same, often one square or a vyama. Examples of the same include a square, the grihapatya, the daily altar, which was typically square or circular. We did see that the square and the circle can have the same area. The ahavanya altar was also square, used for general offerings. Then we have the semicircular. The Dakshina altar was semicircular. Falcon-shaped, Sienacity, constructed by those desiring heaven or prosperity. A tortoise-shaped, constructed by those desiring to win the world of Brahman. A rhombus-shaped for those wishing to destroy enemies. Now, all these different altars have different purposes, hence the different shapes, and obviously the different measurements for each of them. And if you note that all these shaped altars, you can look here, were very meticulously planned. You can see that nothing is amiss and everything is very, very symmetrical and very well planned. Now, if you were to draw a line in between all of these, you would see that there is a line of symmetry, and with the number of squares and the number of rectangles and the rhombuses and the polygons, everything is very symmetrical. Now, they may have or they do have a specific system for scaling also. That is why everything is so perfectly structured. If you look at the tortoise, the shape of the tortoise remains the same, or the normal tortoise shape, and meticulously planned with the different areas, with the different pedestals and the different steps as we see. And so is the rhombus, the square, and the falcon. Now, all of these in the previous slide that did we see that serve different ritual purposes, hence the difference. What were the units of measurement? How did they measure them? How things were so accurate? The Sulba Sutra defined various units of measurement, such as the ungali, often described as the width of a finger, or 34 sesame seeds. You know sesame seeds, small till seeds, stacked face to face, which were essential for precise construction. Now, the ancient instruments, if you see in the chart, is the measure of a footstep, or the measure of a rope, or the measure of a hand span, which is still commonly used, or the measure of an arm length, including the ungli width. Modern instruments that have replaced all these ancient ways of measuring. We have a ruler used every day. We have a screw gauge used in the physics lab. We have the vernier calipers used in the physics lab. And we have a measuring tape, which measures day-to-day things for us. Let's go on to talk about Aryabhata and Bhaskar now, which Aryabhata is for algebra and Bhaskar is for astronomy. So Aryabhata, he came to be in 476 to 550 CE. Aryabhata was considered one of the earliest and most influential Indian mathematician astronomer. His most famous work is the Aryabhatiya, a concise treatise covering various aspects of mathematics and astronomy. So, how does astronomy relate to mathematics? Everything that the stars and their placement and everything is all measured. It's all mathematics. How about the algebra then? Place value system and zero. While the concept of zero existed before him, Aryabhata's work solidified its use in the place value system, where we had the decimal system, which is fundamental to modern arithmetic and algebra. Linear intermediate equations, Kotaka. He provided a general solution to linear intermediate equations of the form ax plus by is equal to c. So that is the basis of algebra that most of us may have learnt in the middle school where algebra is introduced. A method that Bhaskara later called Kutaka, meaning pulverizer or breaking down, learning it in a simpler form. This method is essentially the Euclidean algorithm. This method is essentially the Euclidean algorithm and is related to continued fractions. Quadratic equations. Aryabhata also dealt with quadratic equations and solutions for them. So there was not only a problem but a solution therein. Astronomy. Earth's rotation, a revolutionary idea for his time. Aryabhata explicitly stated that the Earth rotates on its axis daily, and the apparent westward motion of stars is a result of this rotation. This challenged the prevailing geocentric view where the entire sky rotated. Heliocentrism, which is implied, while his primary model was geocentric with epicycles, some interpretations of his work suggest an underlying understanding of heliocentrism, as he correctly accounted for planetary motion relative to the sun. How we say that sun is the center of the solar system and all other planets go around it. So this theory was not propounded now. This has been there for centuries now. Eclipses. He provided scientific explanations for solar and lunar eclipses, attributing them to the shadows cast by and falling on the earth, dispelling the mythological explanation involving Rahu and Ketu. He also correctly stated that the moon and the planets shine by the reflected sunlight. Sidereal periods and length of the year. Aryabhatta made remarkably accurate calculations for the Earth's sidereal rotation and the length of a sidereal year, very close to modern values. Trigonometry. He laid the foundations for trigonometry by defining sine, ardhajya, half chord, versine, and inversine, and compiled sine tables with high precision, which were crucial for astronomical calculations. Now, how about Bhaskara? He was a co of Aryabhatta. Aryabhatta was a little earlier than Bhaskara. Bhaskara was 600 to 680 CE. Bhaskara was a notable mathematician and an astronomer again, who lived about a century after Aryabhatta. His most significant contribution is his commentary on the Aryabhatiya, known as Aryabhatiya Bhashya, the one which Aryabhata propounded. Now let's see what his theory of algebra talks about. Commentary on Aryabhata. He meticulously explained and expanded upon Aryabhata's methods, especially the Kutaka method of indeterminate equations. Negative numbers, we have it on scale now. Bhaskara was one of the first Indian mathematicians to extensively use negative numbers in his algebraic works. Categorization of mathematics. He provided classification of mathematical operations and various type of equations. So the various type of equations are linear, quadratic, cubic, and those of multiple unknowns. Astronomy. Sign approximation formula. He developed a new and more accurate approximation formula for the sine function than that used by Aryabhata. So he was a tad bit better, which was very useful for astronomical computations. Planetary motions. Bhaskara also made significant contributions to the study of planetary motion and the calculation of eclipses. So here, if you see, according to the Hindu astrology, there is Ketu and there is Rahu, and that we did say that the north end and the south end, and they hold a very large value in the position of the stars and the position of the earth and how it affects us. And then about the eclipse also, there is the position of the sun that's just crossed the summer solstice and begin Dakshinyana. So here you can see that we are talking about a ecliptical orbit around which our earth is moving around, and the effect of the sun on the shadow that it casts upon the earth. With that, we finish lesson 3.1. And here we did talk about Aryabhata and Bhaskara and their contribution largely to mathematics and astronomy, and how both logically mathematics and astronomy are so correlated that sometimes we may feel that astronomy is just out of the blues and doesn't hold too much of logic. But with their presence, with their research, with their theories, with their logic, we do know that astronomy has its very solid base in mathematics. And mathematics in itself as a subject was very developed in the Indian knowledge system of ancient times. Thank you.